So that was a brief introduction about my project. The image on the left is my field site. This is the Cornell Bioclimatic Lab, which is the Cornell one of the greenhouses where some of my human subjects are. So to begin with this project, like the human like the use of pesticides in today's world is like a necessary evil, and it's mandatory also because the use of pesticides also kind of ensures food safety, which is very important for human existence. But on the contrary, excessive use of pesticides on a commercial scale is also harmful to humans. The harmful effects of pesticides has been heavily is been well documented by researchers, and for human beings who handle pesticides on a daily basis, which is largely pesticide applicators working in the fields, farm workers. Um, there are three possible entries for the contaminants into the human body. The first is when human beings come in physical contact with the pesticide. So the entry of the pesticide is through the human skin. The second is entry into the body through food, that is ingestion, and the third is through breathing or inhalation. And my study largely concentrates on the entry of pesticides through the human skin, because the human skin, being the largest human organ in the body, is also the biggest entry point or the biggest channel through which contamination can occur. So in order to initiate, or rather get into the study, I started off with a focus group study with the greenhouse pesticide applicators at their site. And I applied the methodology that I applied for my study was the traditional human factors model, which keeps the human or the subject at the center in close relationship to the tasks that they do and the influence of the task on the individual, and uh, also trying to study the environment within which this task happens. So for me, the user is the pesticide applicator. The task is the task, the various tasks that is involved when a pesticide applicator handles or applies pesticide. And for me, the environment was the traditional greenhouse. The challenges of a traditional greenhouse are there are it's a confined environment which has high temperatures and high humidity along with high radiant heat, um, and all of these factors collectively impose a huge um, thermal burden on the pesticide applicators. So from a preliminary study, there were four major areas of focus that came into picture. That was the heat stress faced by them. The second was the fit and the mobility, which was impaired because of improper design or the material being used for existing coverall design. The third was because of improper coverall sizing and fit, the possible entry points for contamination was where two personal protective equipments met. For example, where the length of the coverall at the sleeves and at the trouser hem did not integrate well with the boots or the gloves that they wore, or the area below the neck where the coverall collar did not meet the face mask properly. So these were possible areas or channels through which contamination could enter the body. And the fourth area that came into picture was because human nature is so different, and every individual, in spite of having proper training, has a different way of interacting with their environment and the tasks that they do. So the differences in behavioral responses could also be a reason for contamination. So in order to supplement the study, what I tried to do is, because there are n number of coverall manufacturers in the industry, I tried to map the sizing chart that they offer in the industry, um, and map it to the population data. So the red dots that people see on the screen are actually each individual people, and the graph is plotted of the weight against their height. So, and in order to study this data, I used the Size USA data. The Size USA data is a commercial human anthropometric population data for the US population. It comprises of around 6,000 female and 3,000 male population. So I used that study to see whether existing commercial coverall manufacturers are catering to the body types in the market currently. So the red dots that we see, the square blocks that we see are actually the small, medium, large, extra large, and so on and so forth sizes being currently offered. And the red dots that we see outside those boxes are the people or the sizes of people. In this case, there are male. So the males who are currently either um, like not being covered by the sizing chart commercially being offered. And similarly, if we see there's a huge population of female who fall beyond the sizing chart collectively being offered or provided by the coverall manufacturers. So uh, probably this mapping scenario also gives us an idea that because um, these populations are not being covered currently by these commercial manufacturers, there is a huge dissatisfaction among the population in relation to people not being able to find the correct coverall fit for their work. And in terms of behavioral responses that I just talked about earlier, when video analysis of different pesticide applicators were done and studied, it was for the same task, it was observed that somebody wore somebody like this is a doffing sequence. A doffing sequence is when a person tries to come out of their protective clothing. So in the first instance, we see on the top left, this particular individual in the yellow coverall gets rid of his green protective gloves and then proceeds to take off his other PPE. And whereas in the second case, we see that individual holding on to his inner set of gloves before he takes off the last piece of PPE, which is the face shield that he's wearing. So in the first case, you see that the first individual kind of contaminates himself in the first task that he does, as compared to the second individual who logically is kind of doing the right process of the doffing sequence. So these patterns were observed with the first set of pesticide applicators that we worked with. And based on the first focus group study, as I said, the three broad areas of research that kind of emerged were the first one where I tried to look into developing a sizing system for existing coverall existing pesticide applicators. Why the need to get into this direction was because in order to improve any kind of an intervention looking into improving their fit or mobility or their dissatisfaction with the coverall sizing was because the existing coverall fit and sizing is largely dependent on correcting the existing sizing system. Once you have a proper sizing system, you can always add design features to it to add more features or value to the overall design. So in order to extend that study, I again resorted to using the Size USA data, and from the population data, trying to arrive at a mean um, sizing chart for both the male and female population. And in order to uh, extend this study, once the sizing chart was extracted from the population data, it was put into a simulation software, so this simulation software is the CLO 3D software, which is largely used in the apparel, retail, and fashion industry. So the advantage of this software is you could feed anthropometric measurements, create your own digital avatar, and then do your fit testing on a virtual model. So once I had the measurements, I proceeded on to developing virtual avatars for both the male and female population. Once these avatars were digitally developed, a fit testing was done for coverall sizing. So what the avatar also allows you like dynamic body movements where you could fold your limbs or your torso or your lower limbs, do movements to see how much of stretch and extension and how much of allowance you needed for the coverall in order to accommodate that particular sizing of that particular population. So from once uh, we had satisfactory results from the fit testing, the three-dimensional patterns were converted into flat patterns using another software called Optitex, where grading was done and the fit chart was developed. Now, the fit chart, once the fit chart or the sizing chart was developed, it was also commercially compared to the existing charts to see what and where the problem areas were. So once these charts, once a new measurement chart was developed, our next task was to evaluate and see the effectiveness of the new sizing system that we were working on. So in order to do that, we invited human subjects into our laboratory where we did human subjects. First, we identified, because we were working on a unisex coverall sizing system, we identified those individuals from the sample population that we had, invited them into the lab, and we conducted standard protocol test movements to see the range of movement flexibility that the new coverall, the new sizing chart that the coverall offered. So this was done in accordance to an industry standard, which is the ANSI 101, where the ANSI stands for the American Standards National Institute. And so these were the videos that I was talking about. So the videos are two individuals who wear a size medium on a daily basis. So on the left is a female, and on the right is a male individual. They are performing the standard set of body movements, and we are trying to analyze if there are stretch and stress areas within the garment. So these were qualitatively validated and also quantitatively validated, because if we see closely, the individuals are actually wearing the 3D motion capture system. So the motion capture system also allows us to actually calculate a range of motion for each and every joint angle on the body. So that study was further complemented with digitally 3D scanning these individuals, because what we realized that a big problem with people's dissatisfaction was not just the sizing, where the human anthropometric body measurements were taken, but what we failed to include in the measurement study was uh, because these coveralls are worn over regular clothing, the cross-sectional measurements of the 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 vertical torso, which is basically the measurement from the base of the neck, uh, like from the front to from it goes below the crotch and comes all the way back to the neck at the back. So those cross-sectional measurements, if we see from for the male individual uh, and for the female individual, they they are really important in including these cross-sectional measurements into the measurement chart. So that is known as the torso girth, and also girth or cross-sectional measurements of areas like the biceps, the upper thighs, the cross-sectional measurements of the upper hip and the lower hip areas, which are traditionally not taken into consideration, but are very important factors that should be included in the measurement chart uh, for the new coverall development. So, so these were the findings from that study, and the measurement chart, the findings from the 3D scanning were then incorporated in with the new design features that we were trying to propose that would uh, take care of the issue of growth and flexibility, because these individuals do a lot of range of motion along the upper limbs and both the lower limbs, and a huge amount of motion also happens with bending around the hip area. So we were trying to see how with minimal joinery we could offer those range of motion by adding design features into the coverall design. So there were things like eliminating or having minimal seam under the underarm, which would eliminate areas of stress and strain, because the underarm was one area where there was a high number of reporting of tearing along the underarm seams, the crotch seams. So we tried to provide a continuous seam or gusset along the underarms for both the upper arm and the lower arm. We tried to add pleats along the continuous waist, which could allow vertical growth whenever there was hip flexion, extension along this plane. Uh, and also adding features like shoulder pleats, which could allow more range of motion along the stress and strain along the shoulder flexion, and uh, flexion and extension along the knee and the elbows. So like pesticide applicators, in order to fill the gap where we earlier kind of found that there was the interface between different items of clothing like the face mask and the coverall, where the gloves and the sleeves of the coverall or the bottom hem. So we tried to uh, look into that area by adding design features where there was better sealing between these interfaces. So whenever there was extension of the arms or the legs, or extension or flexion or extension of the neck, this seal was not broken, which offered pesticide applicators better protection against while they were working in a contaminated environment. So that brings us to the third area of my study, where heat stress is a big issue with any individual working and wearing chemical protective suits. We kind of overcome or see this problem with healthcare workers who are currently on the line. So to throw more light into that area is so the degree of the range of pesticides being used in the industry, it varies from low toxicity to very high toxicity, and the correlation is that so pesticides that have low toxicity require coveralls or PPE with minimal number of or minimal requirement in terms of the protection it needs to have in order to protect that individual from the contamination. But as the degree of toxicity increases, uh, the the coverall properties also begin to change. So if earlier the toxicity was low, the coverall design or the coverall material could be more permeable, as in permeable in terms of allowing moisture and heat to escape from the inside to the outside. But as the level of toxicity increases, the coverall design or the coverall material also starts becoming more impermeable. So the more impermeable the coverall design is, the more is the heat buildup inside the coverall suit. So that requires cooling solutions that need to be provided inside the coverall so that thermal comfort can be maintained and the individual can effectively perform their activities without facing any issues of heat stress or heat fatigue. So there were two directions that were looked into in terms of offering cooling solutions. So the one on the right is offering cooling solutions by through design intervention and through proper material choices. And the second cooling intervention was looking at existing cooling solutions in the market and how they could be adjusted or incorporated to allow greater thermal comfort to pesticide applicators. So looking at the first option, when an option where design could play a big role when the thermal load is low, I was trying to integrate gussets or more breathable panels into the coverall design by selecting coverall materials where one fabric material was more um, allowed more moisture and air to pass through, whereas the other material was which was more resistant to liquid spills. So the areas on the orange that you see are areas which use a more permeable fabric which moisture and heat from within the body to pass out, whereas the fabric that you see, the white fabric that you see, is a fabric which is more resistant to liquid spills and more impermeable to entry of any contaminants inside the body. So that was option one. The design option two was what about when the thermal load or when the chemical protective suit needed to be more impermeable, or when the individual walked into an environment which had a highly toxic or a more toxic chemical being sprayed. So could we uh, keep that individual cool by offering or looking at cooling solutions? So uh, so this is the design option in terms of the coverall design, and the individual is wearing a powered air purifying respirator. So what this equipment is you can wear this in a contaminated environment, and the device sucks in air or sucks in the contaminant air, but it has air filters which purify the air and then blow the cool air inside the chemical suit. So the what we found is that in spite of it being effective in working in a confined environment, if the immediate environment had a high radiant heat or was a high temperature itself, then this device would not be effective at blowing cool air inside the suit and keeping the individual thermally comfortable. So in order to complement that, we introduced a conductive cooling device. So a conductive cooling device works on the principle of peltiers. So uh, it works on the principle of conductive cooling, where there are ceramic plates which are in close contact with the body, and it's also battery operated. So uh, both these devices can allow greater mobility to the individual without being tethered to a liquid cooling device or an air cooling device where there would be mobility impairment. So the conductive cooling device, um, like you can select the degree of cooling, keeps the individual cool. So if the PAPR or the powered air purifying respirator is used in conjunction with a conductive cooling device, uh, this hybrid cooling device can collectively keep the individual comfortable in a environment which has high levels of toxicity. So in order to so these two systems have been individually tested in a lab setup and in an actual working setup of a greenhouse. But we are also taking forward this study into a laboratory setup where we are using a thermal mannequin. So a thermal mannequin is basically a dummy which behaves more like a human being in terms of its in its response to its immediate environment. So you control the environmental parameters of temperature, humidity, air movement, and and you make the thermal mannequin wear the set of protective clothing in that sequence, and then we can test these ensembles in three different scenarios, one with very low thermal load, the second with a medium thermal load, and the third with a very high thermal load. And in these three setups, we can use our configuration of using a powered air purified respirator with and without the cooling vest, the conductive cooling vest that we are developing, and trying to see the efficiency and the efficacy or the cooling effectiveness of the hybrid cooling system in an indoor environment or a simulated environment um, of the thermal mannequin, and trying to test the effectiveness of their cooling and trying to see if this kind of a device could be further explored to offer cooling solutions to people engaged in pesticide application in a confined environment of a greenhouse. So these tests are on. We are in the process of collecting more data because somehow because of the COVID situation, we could not run human subject tests anymore. So we are resorting to using means of like the thermal mannequin could be an effective mean for us to get some results, which at a later date could be extended to the actual human testing platform to see how well it behaves. So these are largely the three areas that I have been working on. A lot of data has already been collected. We are still in the process of collecting some more data and some more evidence to support our findings. And and also there are some other design features that have been incorporated into the product development phase, where instead of using a straight front opening like the traditional openings for coverall design is an opening in the front. So the problem with having a front opening is that, like the healthcare workers or pesticide applicators are exposed to liquid spray from the front, and if you have an opening, a vertical opening, then there is a higher chance that water droplets might enter through the vertical opening. So in order to overcome that issue, we tried to give a horizontal, a diagonal front opening. So the idea is that if there were liquid droplets on that fall on the coverall, uh, they trickle down if there is a diagonal opening rather than entering the coverall through the front opening. And then there are storm flaps. There are extended flaps that are being provided to cover the zipper opening. So there is a flap inside and there's a flap outside. So the double layer also adds added protection to the coverall opening. We have introduced gasket for the face shield, because the gasket offers a better seal against the face shield. There were openings. There are ideas of taking the opening towards the back, because you are working largely when you are applying overhead sprays or spraying on the front. There's a higher chance that the droplets are towards your front. So having an opening at the back kind of takes away the problem of having that front opening altogether. It's much safer and much effective. The only problem is that you need a buddy system to help you get in and out of a coverall design like this. There were options of using seam sealing tapes. So in the case of traditional stitching, which uses the needle and thread to join two pieces of clothing. So those seams are taped with a heat seam sealing tape. So that completely seals off the openings or the punctures caused by the needles. We see this very much in our everyday rainwear that we wear. So that system has been incorporated into coverall designs, and using accessories like liquid resistant zippers, if at all they are used in the coverall design. So these were some of the features that kind of are add-ons and ergonomic features and design features that could be incorporated to eliminate the contamination, or keep the pesticide applicator more safer in their existing working scenario. So with that, I would like to acknowledge the project being funded by the US Department of Agriculture. And with that, I would like to take questions from the audience.